All right, welcome to the last day of the Formal Methods Week that we have here. I'm excited to introduce this morning's keynote speaker, Hadas Kress-Gazit. Of course, she has an amazing and admirable CV. She's won the NSF and DARPA Career Awards, as well as awards for teaching excellence. So I'm really looking forward to the style of her talk here because I know it will be wonderful. But my favorite feature is the foundational contributions that she has made to the combination of robotics and autonomy with formal methods. So we were just talking about her website, which she's in the middle of updating, but it's verifiablerobotics.com, which I think also tells you a lot about the theme that runs through her work. So she's a professor at Cornell University with a named chair and a new associate dean of diversity and student affairs. So academic affairs, I apologize. So anyway, without further ado, it is so wonderful to have you here.
Good morning, everyone. Thank you so much. That was such a lovely introduction. I'm also very honored that you made it after yesterday's events. I heard it ran. It was a lovely evening. So yes, so I'm Hadas Kress-Gazit, and you know I was preparing for this talk, and it was a hard topic for me to make. And the reason for that is that I'm typically used to presenting in a kind of robotics, autonomous systems, cyber-physical system venues, where I need to motivate the formal methods and why formal methods is suitable for robotics or some aspects of robotics. And here, don't really need I mean, I have a feeling that you're all sold on the formal methods. And really what I want to do is kind of bring up the robotics and what it is that's challenging about robotics and what is it that the way I've been thinking and how my thinking evolved over time in the context of how formal methods can impact the field of robotics and autonomous systems. Okay, so you know, whenever I make a talk, I try to think about what is my purpose of the talk. I mean, what is it the thing that I'm trying to convey? And some talks are you go with one line of work and you go deep. Another option, which I tend to like better in this kinds of contexts, is to go breadth. So what I want to do today is I want to give you some of the challenges, some of the things that mainly my group has done. I'm going to show a few other people in this context of robotics and kind of tease out a few nuggets of how I see formal methods impacting robotics. And then I want to end with where I see kind of the future, or that maybe see the future might be a little too much, but the things that I'm excited about in the context of formal methods and robotics, and especially kind of towards human-robot interaction. So that's the plan, okay? So I was thinking about this, and I, you know, again, thought process of what does it mean, formal methods, robotics, and then I kind of came to the realization that I want a definition for formal methods, right? So I went to this wonderful paper. I don't know if any of the authors are here, but I really enjoyed this paper. It was awesome. And in that, there's a small definition of formal methods. So mathematics-based techniques for the specification, development, and manual or automated verification of software and hardware systems. So I really like this definition. I don't know that this definition is exactly how I think about in the context of robotics, so I'm going to expand a little bit on this definition and kind of play with it a little bit in a second. But before then, I'm here, I feel like I'm representing robotics, so I must show you some videos, all right? So let me start with this. How many of you know about the DARPA Robotics Challenge? Very few. Okay, not as to be expected. So in 2015, well, the finals were in 2015. DARPA, which is a funding agency in the US, they tend to run these challenges. So the most famous one would have been the DARPA Urban Challenge, which really started the autonomous vehicles boom. So that was in 2008-ish. And what they did after the Fukushima reactor disaster, they came up with a new challenge, which was, can we have a robot perform different tasks in the context of disaster relief? So they came up with this competition that had the robot do 8 tasks. It was walking over kind of sand, getting out of or driving over sand, getting out of a vehicle, opening a door, turning a valve, picking up a drill, walking over uneven terrains, walking up steps, and I think I may have missed something, but maybe not. So those are competitions. There was a final event. I was involved with one of the teams at the time. And this is a compilation that ran the first, this is a compilation that was done by IEEE of the first day. And what they did, they compiled a whole bunch of failures. So I want to show you the failures, and I'll highlight a few things to kind of start to give you the idea of what we're dealing with in terms of robotics. And this is 2015, so things have evolved since then. But the concept of the failures, or the categories of the failures, are very similar. All right, so we started with kind of walking, right? So there's notions of stability. There's notions of, opening a door. Maybe you opened the door and maybe you didn't quite. Again, you'll see a lot of robots falling because these are big, heavy machines that need to stabilize and all of these, DARPA was really into the humanoids at the time. So there's a bunch of things happening, walking on sand is difficult. And of course, I'm showing you, there are a few people that did very, very well, not my team. Walking up steps, again, stability, heavy, it's not, center of mass and all that. But there's some, you'll see, this is, in this case, there was a sensor failure, actually. So it wasn't at the controls, but the sensor was giving wrong information. There's some things falling. This one I really like. It's trying to turn the valve. It's grasping, not the valve, and then it's turning it, right? So had it grasped the valve, it would have been totally fine. There's a whole bunch of other ones falling, things falling on them. And this is a really nice one. I really like this one. So this was human error. The mode switching was not correct. There are different modes. And what happened is it was trying to, well, it doesn't really matter what was happening, but there was a mode switch that was done incorrectly, human error, caused the robot to fall. But interestingly enough, this is the MIT robot, two things that were really fabulous about that. First of all, the task was have the robot leave the car and land and kind of step out into the yellow box. So they did get the point because the robot is fully in the yellow box. So that's great. The other thing, which I think is even more amazing, is it broke the arm. All their testing, or most of their testing, was done with the right arm, all the tasks. There's some tasks that were bimanual, but most of them were unimanual. Because of the algorithms that they had that, so this was led by Russ Tedrake at MIT, because of the algorithms they had, they basically switched them to the left arm, and they were able to complete it. Well, they didn't complete the bimanual one, but they completed the rest of the tasks, which was really amazing, the fact that they can switch so quickly. Okay, so now you see, humanoids, they're complicated. Not all robots are humanoids. Most robots are not humanoids, despite what you may see in the media these days. So what did we see here? We saw kind of environment. So, I thought I grasped the valve. I'm exerting force, I'm falling. There's stability, so the control algorithms. There is the environment. Walking on sand is more difficult than walking on asphalt, and so on. In addition, this is robots. You don't see any people. This is autonomous robots working in the real world, no people around them. What happens when you introduce people? So this is a fairly famous paper from the HRI conference, the Human Robot Interaction Conference, 2015. What they did, these are researchers in Japan. They put a robot in a shopping mall. And they let it kind of, I don't remember how long, but it was a long deployment. So they let kind of just people interact with it. And what you see here is kids, you'll see in a second, basically kids giving the robot a really hard time. So they're blocking it. They're kind of, at some point, they're kicking it. This is interaction in the wild with people. So this is robots around people, where people are not behaving well. So this adds more challenges, people not behaving well. But this is rather extreme. So, I mean, this is a good anecdote, but this is not rather extreme. What I think is more interesting when you start putting people, because robotics really kind of, the idea is to work with, around people. There are other things, and this is an example of work from my colleague at Cornell, Professor Bhattacharjee. He does a lot of work on assistive robotics. So for one of the example tasks that he has there is feeding. So a robot arm with a fork going towards your face and putting the fork in your mouth. Now, this is for people with motor impairments, so spinal cord injuries, multiple sclerosis, cerebral palsy, all these things. And what you'll see here is these different examples of his system being deployed with actual users. So it's not adversarial. I mean, the kids of the robot, adversarial. But the safety that you need to show, and not just safety in the sense of you're not going to poke them in the eye, but rather also the perceived safety. You have something coming towards your face, right? You don't want it to come like, there are directions in which you want it to come. There's a speed in which you want it to come towards your face. You don't, even if it's guaranteed, verifiable, safe, if it's coming very quickly towards your face, you're going to be going like this, if you can. Not these people, some of these people can't. All right, so this gives you a little bit of an idea of the challenges that come with robotics and formal methods, right? We want to guarantee things. We want to specify things. We want to find beautiful mathematical formalisms to be able to say things. But we have physical systems that are messy, right? Different layers of code, from low-level controls to high-level behaviors. We have the environment, right? So the environment may be unpredictable. And worse than that, I don't even know what the environment actually is, because this is all through perception. This is all through my sensors. Am I seeing you guys? Yes, I'm seeing you guys. Can I detect faces? Yes, as a person, I can probably detect faces. If I put a robot here, does anything in the background, does it recognize, whatever, right? So there's the question of perception and errors and uncertainties coming from the perception piece of it. And then there are people, and people, right? So, yeah, say no more. Okay, so going back to the definition of the formal methods, I would like to adjust it a little bit for my perspective. So it could be that, I mean, this is a very broad and very concise, lovely definition. When you think about robotics, the specifications, you have to think about the abstractions as well, right? I take this physical system, this continuous systems with people, with environment, blah, 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 and I need to abstract it somehow to be able to say anything. And what are these abstractions? So abstraction and specifications have to be together. This is not a general view. This is my preferred use of language in this case. So I'm not going to call it development, but I'd really like to think about synthesis. So going from a specification to the system. And we'll talk a little bit about that. And that's been, historically, that's been most of my group's work in the synthesis aspect. And then finally, verification. I want to expand a little bit the definition of verification to include things like falsification. So not necessarily, so starting out, as a young PhD student, I was talking about synthesis for LTL, and I was talking to some colleagues in robotics, and they would look at me and say, nah, not gonna work. What happens if this happens? What happens if this happens? So, and they're right. I mean, they're half right. That's a different conversation to have. But really, the value that I see in formal methods coming from the robotics perspective is not so much the verification. This will always work, okay? But rather the things that I can learn about my system through verification techniques, such as falsification. Can I find counterexamples? Are these counterexamples interesting? Are they real? Feedback. Can I just provide information to the user saying kind of what could go wrong? Under what conditions am I allowed to say that the system will work? And then repair. Can I do this iterative process of something breaks and I use formal methods to repair it? And I'm going to give examples of all these things, kind of the way I'm thinking about that. Okay. So let me start with, so I wanted to start with just talking, I wanted to kind of separate each one of these boxes and talk about them separately, but I really can't, so I'm going to lump in specification, abstraction, and synthesis together. So what I want to do, I'm going to give you a few examples of systems and tasks that we did in my lab over the years, and just kind of comment on what the abstraction was, just to show you the breadth of possible kind of systems that we can look at in terms of this. And I want to talk about the specification languages that we typically see in robotics. In the planning community and the hybrid system community, you might see slightly different logics, but this is kind of coming from what you would see typically in robotics conferences. So I'm going to have a few shameless plugs. So first, this is there's a journal, annual reviews. There's an annual reviews on controls, robotics, and autonomous systems. I was on the editorial board, no longer, but it's there's a whole bunch of really lovely review articles that I highly suggest. I'm going to show a few, I'm going to point to a few other ones. But this is something that we wrote in 2018 that gives kind of an overview of synthesis from the robotics perspective. So what abstractions, logics, synthesis algorithms, and so on. Okay, so I was there, I don't remember who I was talking to yesterday, but almost, I think, more than 90% of the talks I give have this specific slide. So this specific slide has been with me since my PhD days, and I'm like, well, I changed the font because whatever. I'm not going to talk about this because I feel like I don't need to talk about this in this context, context. But LTL, linear temporal logic, is something that's used. If I was thinking about two logics that are used in kind of a robotics context, LTL would be one of them. Everything is discrete, right? There's no notion of time. There's only next. We don't typically use the next because it's kind of hard to think about what next is. Well, kind of. So these are a few systems that we did, that we used over the years, that we've synthesized over the years. And all these are based on, all these were synthesized using LTL, a lot of it with slugs, Rudiger's baby. So let me kind of walk through them. So top left are modular robots. Modular robots are robots built out of these modules, for lack of a for a different word. These modules, each one of these blocks has 4 degrees of freedom. It has 2 wheels. It has a pan, so 3 rotational, and then it has a hinge in the middle. And what it also has, on each face, you can see kind of the half moons. Those half moons are electropermanent magnets that you can turn on and off. So what the systems allows us to do is to reconfigure the shape of the robot. And we can reconfigure this shape autonomously. So what we're doing there is high-level behavior for modular robots, where our abstraction was configurations and gates. So the shape, we had basically a library of shapes, and each shape had a few gates associated, so a few types of motion associated with it. In addition, we had a perception system that abstracted the environment, so stairs, a floor. What else did we have? We had one more thing. We had like a tall thing. And what we wrote is we wrote specifications. Let's see if it works. Yep. We wrote specification to kind of, in this case was search for a pink tag. So we kind of simplified some of the perception from that. And then drop something that's, that's held by the magnet over there. Now the thing is, in that configuration, it can't go upstairs. So it had to reconfigure. So basically it had to drop some of its modules, reconfigure, go up the steps, drop something, and then come back. And this is fully autonomous, okay? So, and then come back, but in this snake configuration, it can't turn. So it needs to add those extra modules back. And it's doing that with the QR tags. And by the way, notice this is ×8. Always look at the times when you're looking at robotics videos. It reattaches and continues going. Okay, top right. We have robots moving around the environment. The abstraction here is regions. I can move from one region to an adjacent region using low-level controllers. That's very well known, not difficult to do at all. What we have here, we have 2 robots. They're working in the same environment. They're not collaborating. Each one of them is trying to go to the flag in its own color. So orange is going to the orange flag, blue is going to the blue flag, and they're not allowed to be in the same region at the same time. Why? Because we're trying to make a point. So in this case, each robot has its own specification. They're not collaborating. But when they see a conflict, they're allowed to exchange part of the specification. So this is LTL. They're really exchanging their assumptions. So if this is within GR1, you think about assumptions and guarantees, you're allowed to exchange the assumption. And then we have this process in which they automatically resynthesize if they can and continue. So if the top right, what you'll see is it kind of moves a little bit fast. So they start moving, they figure out there's a conflict. This one gets out of its way, goes around. Now, it's definitely not doing the most optimal thing. Absolutely not. But it's doing the correct thing. Okay, so the question of optimality, correctness, that's kind of something that to kind of play around with. All right, that's going to loop, so ignore that for now. Bottom left, Baxter, picking up blocks. The abstraction there is a pick up and drop. I have skills that are able to pick up these blocks. It's a very simple, so it's these robots have grippers, have like parallel grippers, red and blue, very easy to detect, pick and place. What you'll see, the specification here was put the blue blocks on your left, put the red blocks on your right. That was the specification. What you'll see happen is it's going to pick up the blue block, and we did some extra work on assumptions, and so it's a little more interesting than that. Again, everything LTL. You would think it would drop the block now, but no. It's going to go and pick up the red, and then put it on top. And this is real time. It's going to pick up the red. It's going to put it above the bin. And then I think it's going to drop the red, and then going to drop the blue. It's dropping the red. Yeah. So it's dropping the red, dropping the blue. This is correct behavior. Is it what you would expect when you look at it and you say put the blue in the left and red in the right? No, right? You expect to pick the blue, drop the blue, pick the red, drop the red. And this is where we go into this kind of perceived safety, perceived correctness that really matters if these robots are working with people. If it's in the factory somewhere, we're not looking at it, nobody cares. But if you're looking at it, you're just like, wait. And also it's slow, and you're just like, what's going on? There's this kind of element that you need to kind of take into account. The final one on the bottom right, this is swarm behavior. So the abstraction here is, I don't care about this individual robots. What I care about, swarm and subswarms. So I want to kind of, given a set of robots, given a specification that requires robots to be in different locations, how do I automatically generate individual controls for these robots such that I avoid collisions and also kind of satisfy the high-level behavior? And what you'll see here, again, not a super interesting task, but the colors represent the subswarms that we had to create based on the specifications. The yellow one, you can kind of see the one that looks like it's lost. That's actually controlled by a person, by my student, and it's acting as a dynamic obstacle. So they kind of to show the collision avoidance. Okay, so but here the individual robots don't matter. The abstraction is over swarms. It's over kind of the group. So this was to kind of show you a little bit of give you a little bit of a feel of the types of abstractions we can look at, the types of tasks we can look at. The other type of logic that we use, and the reason I have the yellow there is to kind of highlight the difference between. I mean, this is again. I'm hand wavy, but to get the intuition, this is the kind of main difference in terms of things I could capture between STL and LTL. How many of you have seen STL? Okay, good. So for people who have not seen, I'm assuming everybody knows what LTL is, but if not, I'm sorry, I'm not, yeah, well, okay, I'm going to go with you. STL allows you to think about continuous signals. So really, now you're talking about predicates over continuous signals. So now I can say things, you know, I'm within 1 meter of the table. That's a predicate. Currently, it's true. Currently, it's false. And then I can start, that's one aspect. So I can talk about continuous signals. And the other aspect is I can start talking about time. And, you know, I can think about continuous time. Nothing is really continuous. We think about discrete time systems. But anyway, we can start doing things that capture distances that don't require me to make a discrete abstraction of, okay, this proposition is within this distance, this proposition, and so on, and start thinking about continuous signals. And the thing that's even more exciting for me, for STL, is the quantitative semantics. So it has Boolean semantics, true, false, but it also has a robustness, or has a robustness measure that tells you how far away you are from either falsifying or satisfying, violating or satisfying a specification. And we can use that for many things, but we can also use that to kind of make decisions about how to be more robust, which allows us to kind of take into account some of the uncertainties that happen in the context of robotics. So a few things we've done with that. So really what we've done is we kind of looked at, created this event-based STL. We added this kind of additional discrete structure that allows us to connect events in the environment. So some Boolean or some propositions that represents events in the environment, and STL. So allows us to express a little bit more things that matter to us. Top left, what you'll see is a user state. So this is we did this. David did this as part. That was his thesis. Top left, what you see is a user study that we did in terms of what types of behaviors would be useful for a robot in a disaster, in a evacuation scenario with novice users. We were going to do this physical, pandemic hit. We did this virtual. So this is a user study that ran. You'll see kind of a robot moving around the environment. I can't really watch it because I get motion sick. So if you get motion sickness, don't look at the top left. It's basically interacting with the person who's controlling this simulation. And we had two different behaviors, and I don't need to sell it to you, but the way I sell it to my community is basically to create those two different behaviors. The only difference was a few symbols in the specification. We basically synthesized this, synthesized that, and the difference was a few, like literally, a few symbols. So we did that with a user study. We also did that with kind of a multi-robot situation, which you can see kind of a few robots moving around. The green, the bottom one, the lighter one, it's green. That was controlled by my student. Just to show you kind of we can have multi-robot scenarios and so on. Well, I'll come back to this to show a different point. So LTL, STL, we've been looking at it in the context of synthesis. People have been looking at this at the context of verification. And also a lot of people have been looking at the specification language in different contexts as well. So to some extent, mining specification, learning specifications from demonstrations. And I mean, this is just, I literally Google searched, I know some of these papers, but this is robot learning and temporal logic. And we can come up, and you'll see here a lot of LTL, STL, those are kind of the main things that we see these days. All right, so that's a little bit on the specifications and synthesis. The verification side, falsification, feedback, and repair, I want to kind of give like examples of what these things, how we've been thinking about these things. And I think this is very powerful. This is very powerful, and and I think people are also, people who used to be, for all methods, robotics, are starting to warm up to that a little bit. So I really like this. So this is from an IJR paper, Webster et al. I really like this image of, or this figure of kind of thinking about verification in the context, because this is the context of human-robot interaction. So formal verification, simulation-based testing, experiments, and then you see the complexity grow in the system, complexity grow in the environment. So this is a really nice figure. The only thing I want to say is that really the things I'm going to talk about next actually fall there. So we're looking at simulations, but we still have logical specifications. So I want to kind of give a taste of that as well. The first thing I want to show, and this is not our work, this is work by Sanjit Seshia's group at Berkeley. So they have this, within the context of simulators, they can generate different scenes. So they have a language to create different scenarios. And they have a suite of verification tools, mainly probabilistic model checking and so on, to verify that in the context of a simulation. And this is a talk they gave that Sanjit gave. I can't remember exactly where, but that's the YouTube link. And I really like this. I just basically screenshotted one of the slides in there, because you can see kind of different case studies on different simulators with different kind of, you see falsification. So it's not so much that we're verifying, but rather we're trying to find counterexamples. We want to trying to find counterexamples that are real, not some edge case that really cannot happen. So that's kind of, so the scenic is the specification language. Verify, they have a kind of a nice acronym, verify, AI, but verify, work on that. The other thing I want to show you is that with a little more detail is work actually for my group. And the idea here is, given a system, given a black box system, given an SDL specification, can you find a counterexample? So the answer typically is yes, simulate Monte Carlo, but can you find a counterexample and can you estimate the probability of failure when you have rare events? So things that are not likely to happen, but instead of doing Monte Carlo, which tends to be inefficient for rare events, kind of guide the sampling in a way that moves you closer to the counterexamples. So here's an example. This is, again, these are not, the task itself is not as interesting, but the process, I think, is. So in this case, we have an arm. This is within a simulator. We used RL to train a robot to pick up a block and lift it above 0.5 meters, which is that green line. Okay, so we trained it. Great, we get a black box controller. Now the question is, does it lift it? So, well, this is the negation, right? So eventually, between 180 and 200 seconds, is the cube more than 0.5 meters above the table? That's the specification. This is STL. And kind of the insight that Guy had in this work was we can actually use the robustness score, so how far you are from violating or satisfying the specification, to guide the sampling in a way that is more efficient to find these counterexamples. For linear systems, we can actually sample rejection-free. For this kind of black box, I have no idea what's inside, there's going to be some rejection, but it's going to be more efficient. So this is the example. The uncertainty here, oh, I should have mentioned, sorry. The main point here is we have some uncertainty in the system. We can use the word noise, but if we have no uncertainty in the system, then we don't really need this. This is in the context of, given a model of uncertainty, what is the probability of this STL formula failing? And what we did here, the uncertainty in this situation is the placement of the block on the table. So we used, this is reinforcement learning. We placed it a few times. We gave it a reward function. It was able to pick it up. And then we try to see what happens with other locations on the table. So what you see here, on the right is Monte Carlo. On the left is what is the work that Guy did. And all the red dots are initial positions of the block in which the task was successful. Black dots are positions where the task was unsuccessful, where the specification failed. And what you can see, Monte Carlo, as you'd expect, kind of covers the space. On the other hand, ours starts to cover the space. You can ignore the blue. The blue are still things that we're not that are fine, but it very quickly starts to make its way towards these kind of counterexamples. Those black dots are counterexamples. And what we find here is now that we have these counterexamples, we can just go and simulate those counterexamples and see what the system is actually doing. So in this case, it kind of turned out to be something interesting. The bottom left failure modes are all, the block just falls out of the hand, out of the gripper at some point, right? So you can see it's picking it up, the two on the left and the bottom right, it's picking it up, it's dropping. The failure modes on the top right are, the arm is unable to go above 0.5 meters. Now, why is that? I don't know, it's a black box, RL, I don't know what happened, right? And are we always gonna see this kind of separation? I'm guessing no. But it's kind of interesting to see, you can go back and kind of and simulate these things to show the system designer what's going on there, and maybe put additional examples and so on. So this is kind of from the falsification. This is going back to the event-based STL. In this case, we are able to synthesize. So this is, once we move to STL, all our guarantees kind of go out, most of our guarantees go out the window, because we're doing, we're solving an optimization problem at some points, and I should mention, for synthesis of STL, there are two approaches. There's the mixed integer programming, which is one approach, which has nicer properties, doesn't scale quite as well. And then there's kind of using control barrier functions. So there's work on that. In this case, we're going the control barrier function route, and we're composing control barrier functions based on the environmental inputs. So we know when we're getting to the boundary of the control barrier functions, we know it's a possibility that we're going to fail soon. If I'm inside, great. So I can't really give a guarantee. Now, I can't really give a guarantee anyway, because in this case, the green robot, which is part of my specification, is uncontrollable by the system. So this is controlled by something external. So in this situation, ignore the robots on the top. Just look at the robot on the bottom. The task here is whenever there's a green robot in this black box on the left, the black robot needs to come to that green robot, and then it needs to guide it towards the end of that, to the rightmost side of this environment. It needs to get there within 60 seconds, but it also has to maintain a distance from the green one. So you can see where I'm going with this, right? I'm not controlling the green one. I need to maintain a distance from the green one, but I also need to make it to the end. So if the green one is not moving, I'm going to violate my specification, right? I have no control over that. So I can't guarantee. What I can do is start to give pre-failure warnings. If I see that I'm starting to get close to the edge of my CBF, close to violating my guarantees, I can start providing those guarantees. And what we did with follow-on work is allow the user to actually change the specification at runtime. Add more time, add a disjunction, these kinds of things. So in this case, what you'll look at, take a look at the bottom. So it's moving. You'll see the pre-failure warnings show up here. So it's close. So the green one is kind of moving slowly. So the black one is kind of maintaining distance, but there it stops because the green stopped. It's going to keep going. And what you'll see in a second, it's closer. Again, the green one is stopped. Starts moving. It's going to move again. It's always on the verge of violating the specification, the black one. What you see here, there's another pre-failure warning. The other pre-failure warning is, now if another green one shows up, I can't make it to the right and still make it to get to the left, to the new green robot. So there's kind of this extra pre-failure warnings that allow us to provide feedback to the user, right? So it's not falsification per se. It is definitely not there's no verification here. It's synthesis that could fail, and we want to give the pre-failure warnings. Okay, the final thing I want to talk about in terms of, before I talk about future work, future directions, is the notion of repair. So we had falsification. Here's something that could go wrong. Feedback, here's something that is going wrong or is about to go wrong. And then repair is, oh my God, something went wrong. What do I do now? So in the context of LTL, in this case, specifically GR1 synthesis, reactive synthesis, what we can do is, well, the setting is, I'm assuming someone gave me a bunch of skills the robot can do. So if you think about it from the planning perspective, it's like it's actions. So we have preconditions, postconditions. This is all encoded in LTL. And now I have a high-level task that I want to do. And now what happens, and I'm able to synthesize. So I have a controller that can compose these skills together to finally generate my task, to fulfill my task. And now the question is, what happens if I didn't do that. Okay. I know, right? And I did not, falsification. I think I know why that happened, or not. So the idea is, what happens if now I can't synthesize, or something happens as I'm executing, and my assumptions, my preconditions of the skills are falsified, and I can't do this. So the idea here is, as either offline, well, it takes, or online in this case, as I'm detecting that there's a problem, can I find definitions of missing skills? Symbolic definitions, but then also the physical implementation of those skills, right? Because I can find a symbolic skill that makes me go from here to Ithaca in one step, right? Not physically possible. So the question is, it's kind of back and forth between the physical and the symbolic allows me to kind of find these missing skills. So in this context, we have a bunch of skills. We have the robot can move, the robot can pick up an item, it can drop an item, but it's making some assumptions. I didn't do that either. It's making some assumptions. So what you're going to see here is that these assumptions are violated. So for example, it was supposed to move that, that pink object to the right, but now there's an object there. So it had to recreate a skill that puts it to the left. I think I'm not going to explain too much what's going on here, but basically what we're looking at is there's 3 skill violations. I'm starting to execute a skill. Its preconditions, its assumptions it's making gets violated. So that cone was not supposed to be there. It's resynthesizing. It's creating a new skill that allows it to complete the task. So this is So the idea here again is finding missing skills, both from the symbolic perspective to fix the task, but also from the physical perspective to actually be able to implement it. Okay. All right. So this is kind of, I'm going to keep my Hadas' definition of formal methods in the context of robotics. It's not that doesn't capture it, but I just want to kind of highlight a few things. So I want to kind of end with a few exciting directions in my mind. So again, slightly biased. I'm going to talk about 2 things. The 2 things that kind of are showing up now, and I had some of these conversations at this conference. The first one is robot learning and formal methods, right? So I know, Marta gave a talk about kind of the verification of neural networks. You can think about verification of a neural network as its own question. And then you can think about the question of, I have a system that has learning in it, be it perception, be it the action. And how do I start thinking about verification? Can I do verification? Probably not, but falsification and synthesis and all these questions on the full system, because I really care about the full system and what it can do. So I said, as I mentioned, a few kind of other plugs for the annual reviews. These are kind of things that, the community, from the robotics perspective, or even the hybrid, people coming from the hybrid systems community and going and kind of implementing these things in robotics, you'll see a lot of the word safety. And safety really typically means you have a set of states that are unsafe. Can you guarantee it? So there's shielding, so safety filter or safety shield. There is safe learning, so limiting the actions in an RL setting, reinforcement learning setting, and so on. We need to move a little bit more towards not just safety, but also liveness. So they're kind of these are really great review articles that kind of show the thinking from about safety from the point of view of robot learning. But I think there's a lot of things to be done there. It's really interesting. The other thing, which I alluded to at the beginning, is formalizing human-robot interaction. So, okay, let me show a quick video. Oh, actually, before the video. So, a few years ago, pre-pandemic, we had a Dutch School seminar on formalizing human-robot interaction, verification synthesis for human-robot interaction. This is a position paper that came out of that Dutch School, which I'm very proud of, this communication of the ACM in 2021. And in it, so this is, if you look at the list of authors, I'm sure there's some names you recognize and some names you don't recognize. And that's because it really was a collaborative paper between HRI researchers, people who do formal methods within robotics and out of robotics and so on. And we came up with a few kind of interesting challenges that I want to kind of leave you with. So before then, I want to show you this video, and I'm going to skip a little bit ahead. The context here is, remember that simulation, the user study in simulation of a disaster kind of robot. So we actually, post-pandemic, ran it. So this is, the robot is controlled using event-based STL, fully autonomous, and so on. So we have the two different behaviors. They're HRI questions, which I'm not going to go into. But what I do want to go into is something interesting. Let's see if I can do that. Oh. Oh, it's not letting me skip ahead. Interesting. Oh. All right, I'm going to run this and yeah, I still have a few minutes. So it's going to have two different behaviors. One of them, it's kind of the robot is initiating an evacuation. It's trying to be proactive. The other behavior you'll see in a second is the robot is following the person decides when to exit, and then they exit. It's a little more complicated than that, but that's kind of the idea. Again, fully autonomous. The way we're doing this, the robot has a laser rangefinder. We map the environment with a laser rangefinder. It does localization. It's detecting the person using a camera and like this wireless sensor. You can see we made the camera's job easier by putting this kind of leg warmer on the person. So it's like red with a green stripe. It's very easy for vision algorithms to detect. But what you'll see in a second, which I found very interesting, is that the notion of safety. So when you run an autonomous robot in an environment without motion capture, they fail. Typically, localization just gets messed up. So you'll see in a second that localization messes up. So the robot thinks it knows where it is. It's not quite correct in its assumption of where it is. And then you'll see at the end there, it basically bumps into the wall and falls down, right? Now, the interesting thing here is that that participant actually gave the robot 9 out of 10 for safety and 8 out of 10 for trust. So there's something going on there in terms of the interaction itself. And even though it's not safe, I mean, it ran into the wall. Running into the wall is not safe. But the person it didn't affect them in a way that made them kind of distrust the robot. So the point I'm trying to make here is that when you think about HRI, safety of the robot and safety in terms of the interaction is not the same thing. I can pick up this, this adapter, and I can, if I drop it a few times, or imagine I'm a robot. I'm trying to put this on the table. I'm dropping it a few times, but then I pick it up and leave it here. It's failing, but it's kind of doing the right thing. You're kind of like, you're like, okay, that looks okay, or maybe some people. On the other hand, if I pick it up, and every once in a while I just decide to put it here, you'd be like, what's going on, right? That would be something broke in the interaction. Both of them are failures, but one of them is going to be more detrimental. So the questions that are coming up in the context of HRI, formal methods and HRI, are how do I specify interaction? Not safety of the robot. I'm not going to run into a wall. But what is it that enables me to have a seamless interaction even under some robot failures? And robots will fail. There's no going around that. The other two are kind of interesting things from the human perspective. So people adapt to technology. So how do we model that? How do we model that from the formal methods perspective? The fact that a person, as they gain more knowledge of the system, will actually help the system or change their behavior. So we can't assume that a person is fixed, right? Or the model of a person is fixed. And modeling of people is difficult, and we can go on a whole long tangent around that, but we will need a model if we want to do any synthesis and so on. So there's the notion of adaptation. So typically we think about a robot adapting to the person, but we really need to think about the person adapting to the robot in the context of HRI. And finally, the notion of variability. People are different. People come with different baggage, right? And the question is, how do we create these interactions that are tailored to the fact that people are different in their capabilities, in their background, in their value system, in their culture, right? Those are kind of things that come up that we need to think about. Okay, so to recap, a few exciting directions I find exciting is connections to learning and HRI. I'd like to, this is all done with students. There's, you can see the length of my hair is shorter the older I get. And then I have a lot of pictures around food. So that's kind of feed your students. And with that, thank you so much, and I'm happy to take questions.
All right, thank you so much. Yes, I'll go for the first question back here.
Hey, Hadas, thanks for the great talk. I was really curious about the initial states for the manipulator robot that you were, so it was reinforcement learning policies, right?
It was reinforcement, yeah, it was RL policy, yeah.
Yeah, so with those, the challenges with reproducibility, right? So with, like when you found an initial state, that rare event, was the seed fixed, or did you have to, like it happened quite often? Like in the sense that, was it just one particular parameter configuration and initial state that made the policy break, and you had to do a lot of simulations to get that, or every time?
So if you remember, the image was a bunch of red dots and then black dots. All the black ones were failures. So the point here was that using the technique that Guy developed, we can guide the sample. So this is also, so I have a simulator. I'm sampling from it. Monte Carlo, I'm going to sample, see what happens. In this case, we're kind of guiding the sampling based on the robustness metric for the specification to move towards those failure modes. Those failure modes, I don't know how many failure modes there are, but in the context of rare events, this is a more, you are more likely, and I have there's other kind of, we show how in a different context, in a different scenario, Monte Carlo, 60% of the time, we ran 1,000 simulations, 60% of the 600 simulations said verify the system, right? All the samplings, they didn't find the failure mode. And for us, I think it was like very, very, very few of those. So it's basically, the idea here is a way to guide the sampling such that you're more likely to find those rare events. And this RL example is, we trained it basically, as you train RL. You initialize, you explore, you find, and at some point you say it's okay.
Yeah, I think so. I think that makes sense. The thing I was like, once you found the counterexample, right? After that, was it you generated the videos, right? Mm-hmm. So those videos, were they like, in the sense, were you able to recreate that counterexample that you found during the search?
That's what you saw.
Yeah, so it was the same one essentially.
Yeah, because the counterexample basically was the uncertainty here was the position of the block. So you put the block in the same place, and then
it happened again.
Yeah.
Okay. Yeah. Thanks for that.
All right. Other questions? Yes.
So thank you for a very interesting talk. I wonder how much it would be related to AI if the robots were controlled by deep learning, say. Would your techniques also work if the arm control was synthesized by by deep learning?
So the example with the verification was reinforcement learning. So it was a black box. So okay, so let me go back. That verification work was give me a system that I can simulate. So I can control the input, I can look at the output. Now the question is, given and I have some uncertainty model. So it could be, we started with Gaussians, then we're with, I keep forgetting the word. Anyway, it doesn't matter. Give me some noise distribution on the inputs. Now I can sample. Now, given this black box, can I find counterexamples? So whatever's in the black box, in this case it was reinforcement learning, could be anything, right? But the point there is that I need to be able to simulate it. Now, how this translates to real world, there's a gap. And I didn't talk about this, but simulation to real world, there's a gap, right? There's a gap. So this is kind of enabling us to gain more trust in the system. And then the question, but to your allow me to expand a little bit on what you were saying. When I start thinking about learning, my soapbox is end-to-end learning. I don't understand why anybody would do that. My soapbox is let's learn skills, yes. Let's compose them using other techniques, and that enable us to start thinking about what happens at the skill level. Can I say some things about the skill level? From the skill level, can I say some things about the full system? So I'm very much in the composition, modularity, use learning for the things that it's really good at, which is fairly simple. Well, simple is a bad word, but skills, atomic skills, and then compose them as opposed to learning everything end to end, because I think that just doesn't scale, doesn't make sense, doesn't.
Okay, thank you very much.
That's my soapbox.
Thanks for the talk. I was under the impression that you have these two levels of representation, the logical level at which you reason and then the lower level at which you are basically acting upon these behaviors. Now, there are situations where maybe you do not know or yet the abstraction of the environment where you will be acting upon. So can you say something about how you would build the abstract representation at the abstract level upon which you would like to reason?
So, I mean, the question of abstraction is a wonderful question. I don't have a general answer for that. The way we've been doing this is we're thinking about, we typically tend to think about events. So my abstraction would be events and kind of what it is that at the specification level, at the task level, I think about events and how the robot should react to those events, right? Because the beauty of temporal logics allows me to put conditionals, to put livenesses, to put safeties and all that. And then what we're doing, we have some work on, okay, so we're assuming these events, we're assuming some abstractions, and then what we're doing is making assumptions about the behavior of that abstraction. Now, if that abstraction, if those assumptions fail, we have a way to kind of rewrite the assumptions. But that's still assuming the abstraction is given, right? Assuming I know what those building blocks are. So your question of how do I know what those building blocks are is a wonderful question, and I don't have a really good answer for that because it is very task-dependent, system-dependent, and to some extent, at the logical level, I have these symbols that I'm going to be using. And if I have a symbol I didn't know about, I don't really have an automated way. I don't have an automated way to incorporate a new symbol. Given the symbols, the behavior of those symbols, that I can automatically adjust. But getting a new symbol, that is something that where you start thinking about those failures and verification and stuff like that. But that is exactly a problem. Yes, that is a real problem in robotics.
Okay, thank you.
Do we have a quick last question? I'll ask you a silly one. You can laugh at me. So Andre and I were talking the other day about the silly ways in which people that we have been near have messed with robots. Like, for example, students at Carnegie Mellon intentionally leading robots roaming the halls to get themselves locked into a closet without knowing it. Or in San Francisco near NASA Ames, where I used to live, how people have developed coning into a sport. So
yes.
For those of you who are not familiar with this, there are people in San Francisco who wait for the autonomous taxis to come by, and they have the orange traffic cones, exactly like, this is what made me think of it, was your video where your student did that to the robot. And they put the orange cone on the hood of the car, and it makes the car get very confused and stop, and there's extra points for making it do this in a really unsafe location where it would cause a traffic accident or be, sort of sideways in someone's way. So,
and that's specifically Cruise. That was Cruise.
Yeah.
That had a really bad accident recently. Yeah.
Yes, yeah. So, what should we do? What's the best next step to fix this problem?
To fix the problem of people? I should mention I live in the U.S. now, and fixing the problem of people is This is recorded, so maybe I won't finish my sentence. But
or
yeah.
just since you're familiar with the coding, do you know
Yeah.
what should they do better
You
to
know,
prevent these accidents?
so it's interesting. The coning comes from the people in San Francisco being pissed off by the autonomous cars messing up their environment, right?
Yeah,
So
yeah.
they drive slow, they stop a lot,
Yep.
they start with making noise in the middle of the night. There's a video that there you see all these cruise car, I think it was cruise, making all this noise in the middle of the night. That is an HRI problem, right?
Yeah.
Why? There's also if we're talking about HRI problems, there's all these delivery robots.
Yeah.
And there was this huge I don't remember what, I think it was last year. There was this huge kind of cry out. Those delivery robots were blocking the edge. When you go from the sidewalk and there's like people in wheelchairs, they have to go down the ramp.
Yeah.
They were blocking the ramp, and people were on the sidewalk, unable to leave the road because those things were blocking. And that is an HRI problem, right? This is not it's someone, whoever designed the system wasn't really thinking about the people interacting with those systems.
Yeah.
So maybe that's a little harsh because they are very good people there and all that, but still these things show up. So I think this makes the point of HRI, right? The point that it could be safe from the robot's perspective, but it's messing up the interaction. And those are kind of the things that, I don't know, it's a hard problem. People are weird. People are, different cultures are different and so on. So don't have a good answer for that either, other than people need to keep in mind people when they're designing technology. And I think not enough people design technology with real people who will be impacted. So maybe that's a broader lesson, not just formal methods.
Well, thank you so much for a really entertaining talk.
Hadas, so to thank you for the talk and as a memento for the conference, we would like to offer you this. I don't know if you heard the story the last few days. This is a designer item designed by one of our alumni, actually. This is actually a corkscrew in the shape of a woman friend of the designer, and there's a story that you can look it up actually on the internet. It's quite interesting and famous, and we hope you like it as a souvenir from the conference. Thanks a lot. Thanks a lot. Okay.